Welcome to another deep dive. Today, we're going to be taking you on a journey into the heart of automotive software. We're going to try to unravel the intricate dance between the AUTOSAR operating system, as the OS, the runtime environment, better known as the RTE, and the basic software mode manager.
It's fascinating to consider that these often overlooked software components are essentially the unsung heroes of your car's electronic brain. They're working tirelessly behind the scenes to ensure everything runs smoothly, from engine control to those advanced safety features that we rely on.
So before we get into the details, let's set the stage a little bit. What exactly are these components and why should we care? How they interact? Can you give us a quick rundown of each player's role?
Absolutely. So let's start with the OS, the foundation of our system. Think of it as the bedrock on which everything else is built. It's responsible for managing tasks, resources, and time on the electronic control unit, or ECU.
Okay, so the OS is like the master organizer, making sure everything runs on schedule and have the resources it needs. What about the RTE? Where does it fit into this picture?
So the RTE sits above the OS. In this layered architecture, it acts as a kind of intermediary between the application software that determines your car's functionality and the lower-level software, including the OS and those essential BSWM modules, like our mode manager.
So the RTE is like the translator, bridging the gap between the high-level application software and the nitty-gritty details of the hardware.
That's a great way to put it. The RTE's primary role is to handle communication between these different parts of the system, making sure they can talk to each other effectively.
All right, so we've got the OS managing tasks and the RTE handling communication. What about the mode manager? What's its claim to fame in this system?
The mode manager is like the stage director, controlling which software functions are active at any given time. Think about the different modes your car has: parking, driving, maybe even a sport mode. Each of these modes requires different parts of the software to be running. The mode manager orchestrates these transitions, making sure the right software components are activated or deactivated as the car switches modes.
It's starting to sound like a complex dance between these three components, each with a specific role to play. But how do they actually work together? What happens, for example, when a software component needs to talk to a hardware peripheral, like a sensor or an actuator?
That's where the RTE's communication prowess comes into play. It provides a standardized interface that allows software components to interact with each other and with the underlying hardware without worrying about the messy, low-level details.
So the RTE is abstracting away the complexity of the hardware, making it easier for the software components to get their jobs done.
Exactly. The RTE essentially provides a virtualized view of the hardware to the software components, shielding them from the specifics of how the hardware actually works. This is crucial for portability and maintainability of the software.
That makes sense. If the software doesn't have to be tightly coupled to the hardware, it's much easier to adapt it to different ECUs or even different car models.
Precisely. Now, within this communication framework, the RTE supports several different types of communication patterns, depending on the needs of the application, for example. You have sender-receiver communication, where one component sends out data, and any number of other components might be listening to receive it.
So sender-receiver is like a radio broadcast.
Yeah.
One signal going out to multiple receivers. What other communication types are there?
Another common pattern is client-server communication, where one component requests a service from another component and waits for a response. Think of it like ordering food at a restaurant. You're the client. The kitchen is the server, and the food is the service you requested.
And the RTE handles both of these, even when the communicating components are on different ECUs.
Absolutely. It uses various mechanisms depending on the situation. For communication within a single ECU, it might use direct function calls, where one software component directly calls a function within another component, or it might use shared memory, where components access data in a common memory area.
So those are more direct methods for communication. When everything's happening on the same ECU, what about communication between different ECUs?
For inter-ECU communication, things get a bit more complex because we're now dealing with messages traveling over the vehicle network. In these cases, the RTE relies on the communication stack, or COM for short, which is a specialized BSW module responsible for sending and receiving messages over the network.
Okay, so the COM is like the postal service, handling the delivery of messages between different ECUs.
A good analogy. Now, the choice of which communication mechanism to use depends on factors like the type of data being exchanged, the required speed and reliability, and of course, whether the communication is happening within or between ECUs.
It sounds like the RTE has a lot of responsibility, making sure all these different types of communication happen smoothly and reliably. But where does the OS fit into all of this? Is just sitting back and letting the RTE handle everything?
Not quite. The OS actually plays a critical role in how the RTE functions. Remember, the OS is responsible for managing the execution of tasks within the system. And the software that makes up your car's functionality is divided into smaller units execution, called runnable entities.
Runnable entities. So those are like the individual tasks that the OS needs to schedule and run.
Exactly. Now the RTE comes into play because it determines how these runnable entities are mapped to OS tasks or something called ISRs.
ISRs, what are those?
ISR stands for Interrupt Service Routine. They're special pieces of code that are triggered by hardware interrupts. Think of it like an emergency phone call that interrupts whatever the processor was doing and demands immediate attention.
Got it. So the RTE is essentially telling the OS how to handle these runnable entities, whether to run them as regular tasks or as ISRs based on their specific requirements.
Precisely. And the RTE also uses events and triggers to control the activation of these runnable entities. For instance, a sensor signal might trigger a specific runnable entity to process that data, or a timer might trigger an entity to perform a periodic task.
It sounds like we're starting to see how the OS and the RTE are working hand in hand to manage the execution of the software and make sure everything happens in the right order and at the right time. But we haven't talked much about the mode manager yet. How does it interact with the OS and the RTE?
The mode manager comes into play when there's a need to switch between different operational modes of the vehicle. These mode switches can be triggered by various events, like the driver turning the ignition key, engaging the transmission, or activating a specific driving mode. And when a mode switch is initiated, the mode manager interacts with both the OS and the RTE to ensure a smooth and safe transition.
This is a coordinated effort between all three components.
Yes.
To handle these mode changes, what specifically does the mode manager do during this transition?
Its primary responsibility is to activate or deactivate specific runnable entities based on the requirements of the new mode. For example, if you switch from drive to park, the mode manager might deactivate the runnable entities responsible for engine control and activate those responsible for parking assistance systems.
So the mode manager is essentially telling the OS, via the RTE, which parts of the software should be running in each mode.
Exactly, and it doesn't stop there. The mode manager also works with the RTE to reconfigure the communication paths, ensuring that the active runnable entities have access to the necessary data and can communicate with each other as needed in the new mode.
It's starting to feel like a very complex puzzle, with all these pieces fitting together in a specific way. But how does the system ensure that all this switching or reconfiguring happens without causing errors or instability?
That's where the robustness of the AUTOSAR architecture comes in. The OS, the RTE, and the mode manager are designed to work together seamlessly, following a well-defined set of rules and procedures to ensure that mode transitions happen safely and reliably.
We've covered a lot of ground in this first part of our deep dive, from the basic roles of the OS, RTE, and mode manager, to the different types of communication they handle, and their intricate dance during mode transitions. It's fascinating to see how these seemingly invisible software components are working tirelessly behind the scenes to make our cars function smoothly and safely. But I have a feeling this is just the tip of the iceberg.
You're absolutely right. We've only just scratched the surface of this complex and fascinating world. In the next part of our deep dive, we'll delve deeper into how the OS and RTE work together to manage resources and ensure data consistency, especially when dealing with multi-core processors, which are becoming increasingly common in modern vehicles.
Welcome back to our deep dive into the world of AUTOSAR. In the last part, we talked about the OS, the RTE, and the mode manager, and how they handle communication and manage mode transitions. It's already clear that these software components have a lot on their plate, but I'm guessing there's even more to the story, especially when we start talking about things like data consistency and multi-core processors.
You're absolutely right. Those are critical aspects of modern automotive software, and they bring their own set of challenges and complexities to the table. So let's start by diving into the concept of scheduling. Remember those runnable entities we discussed? The individual pieces of software that the OS needs to manage.
Yeah, those are the building blocks of the application software, right?
Yeah.
The tasks that the OS needs to schedule and execute.
Exactly. And the OS needs to decide when and how to execute these runnable entities, making sure the right tasks run at the right time. That's where scheduling comes in. It's like a traffic cop, directing the flow of software execution and ensuring everything runs smoothly.
So it's about prioritizing tasks and allocating processor time. But how does it actually work in AUTOSAR? Are there different ways to schedule these runnable entities?
There are indeed, and AUTOSAR offers a lot of flexibility in this area. One common approach is priority-based scheduling, where each runnable entity is assigned a priority level. The OS then ensures that the highest priority entity that's ready to run gets the processor's attention first.
That makes sense. Critical tasks like those related to safety systems would obviously need higher priority than less time-sensitive tasks.
Exactly. Now, the RTE plays a crucial role in this scheduling process as well. Remember, the RTE is responsible for mapping runnable entities to OS tasks, or ISRs, those interrupt service routines we talked about. This mapping essentially determines how those entities will be scheduled by the OS.
So the RTE isn't just about communication, it's also influencing how and when the software actually gets executed.
It's all interconnected. The RTE's mapping decisions can significantly impact the system's real-time performance and its ability to meet timing deadlines. Now, let's shift gears a bit and talk about another trend that's changing the landscape of automotive software: multi-core processors.
Multi-core processors, I've heard that term before, but can you explain what it means and why it's important in the context of AUTOSAR?
Modern vehicles are becoming increasingly complex, demanding more and more processing power to handle everything, from advanced driver assistance systems to in-vehicle entertainment. And that's where multi-core processors come in. Instead of having a single processing unit, these processors have multiple cores, each capable of executing instructions independently.
So instead of one chef in the kitchen, we now have a whole team working simultaneously. That's got to be a huge performance boost.
You got it. Multi-core processors offer significant performance advantages, but they also introduce new challenges. For the OS and the RTE, instead of managing tasks on a single processor, the OS now needs to coordinate the execution of tasks across multiple cores, which is a much more complex problem.
I can imagine. What kind of challenges arise from having multiple cores?
One of the biggest challenges is ensuring that shared resources are accessed in a controlled and synchronized manner. If two tasks running on different cores try to access the same data simultaneously, you could end up with data corruption or other unpredictable behavior.
That sounds like a recipe for disaster. How does AUTOSAR handle these multi-core challenges? Does the OS have some special tricks up its sleeve?
Absolutely. AUTOSAR provides mechanisms to manage these challenges. One approach is to enforce that all tasks within a specific OS application run on the same core.
OS application. What's that? Is it different from the application software itself?
It's a way of grouping related software components within AUTOSAR. Think of it as a container for your application code. And by ensuring that all tasks within an OS application stay on the same core, the OS simplifies some aspects of inter-task communication and reduces the risk of conflicts.
Smart. Keep things local whenever possible. But I'm guessing there are times when communication between cores is unavoidable, right?
You're right. Sometimes communication between cores is essential, especially when you have tasks on different cores that need to exchange data or synchronize their actions. And that's where the intercore communication, or IOC, mechanism comes into play.
So the IOC is like a bridge connecting these different cores, allowing them to talk to each other.
A great way to put it. The IOC, which is part of the OS, provides a standardized way for tasks on different cores to exchange data. It handles all the complexities of data transfer and synchronization, making sure communication between cores is as seamless and reliable as possible.
That's really interesting, and I'm assuming the RTE leverages this IOC mechanism when it needs to handle communication between software components running on different cores.
Exactly. The RTE's job is to abstract away the complexity of communication, regardless of whether it's happening within a core, between cores, or even between different ECUs over the vehicle network. It uses different mechanisms depending on the situation, but its goal is always the same: to ensure reliable and efficient communication between the software components.
We talked a lot about the OS and how it manages tasks and resources, especially in context of multi-core processors. But what about the RTE? Does it play any role in managing resources other than communication channels?
That's a great question. While communication is its primary focus, the RTE also plays a role in managing memory resources. One important concept here is the notion of memory partitioning. The RTE can divide the available memory into separate partitions, each assigned to a specific software component or group of components.
It's like dividing up a house into separate rooms, giving each resident their own space. Why is this memory partitioning important?
It's all about protection and stability. By partitioning the memory, the RTE can prevent one misbehaving software component from corrupting the memory used by other components. This isolation helps to enhance the system's robustness and prevent errors from cascading through the entire software stack.
That's like having those safety nets you see on construction sites. They prevent accidents from spreading and causing widespread damage.
A good analogy. Memory partitioning is crucial for safety and security, especially in automotive systems, where software errors can have serious consequences.
We've covered a lot of ground in this part. From scheduling to multi-core challenges and memory management, it's amazing to see how the OS and RTE work together to handle the increasing complexity of automotive software, making sure everything runs smoothly, efficiently, and, most importantly, safely. But I'm wondering, with all this data flying around between different cores, ECUs, and memory partitions, how does the system guarantee that the data remains consistent and accurate? That seems like a huge challenge.
You're absolutely right. Data consistency is paramount, and it's something we'll delve into in the next part of our deep dive. We'll explore the mechanisms that the OS and RTE use to ensure data integrity, especially when dealing with concurrent access from multiple tasks, or even different cores.
Welcome back to the final part of our deep dive into the intricate world of AUTOSAR. We've explored the roles of the OS, the RTE, and the mode manager, and how they collaborate to handle communication, scheduling, and resource management in the face of increasing software complexity. But there's one crucial aspect we haven't delved into yet: data consistency. With data flowing between different cores, ECUs, and memory partitions, how does AUTOSAR ensure that this data remains accurate and reliable?
That's an excellent question, and it's fundamental to the stability and safety of any automotive system. Data consistency is all about ensuring that different parts of the software see consistent view of the data, even when multiple tasks or cores are trying to access and modify it concurrently.
So it's about preventing conflicts.
Yes.
And making sure everyone is working with the same information. But how is this achieved in practice? What mechanisms does AUTOSAR employ to prevent data from getting corrupted or out of sync?
AUTOSAR employs a combination of strategies, and the RTE and the OS play key roles in this orchestration. One common technique is the use of buffers. Think of a buffer as a temporary holding area for data. When data needs to be transferred between components, the RTE might create an intermediate buffer to hold the data while it's being copied or processed. This prevents direct access to shared variables, reducing the risk of conflicts.
So it's like having a staging area where data can be safely exchanged without multiple components trying to modify it at the same time. That makes sense. Are there other mechanisms besides buffering?
Absolutely. Another approach is data copying. In some cases, the RTE might create separate copies of data for different components, allowing them to work with their own independent versions without affecting the original data or interfering with each other.
So it's like giving each team member their own copy of a blueprint. They can make changes to their copy without worrying about messing up anyone else's work.
Precisely. And then there's synchronization. This involves using mechanisms like mutexes or semaphores to control access to shared resources. These are like locks that ensure only one task can access or modify the data at any given time, preventing conflicts and maintaining consistency.
It's like having a traffic light at an intersection. It ensures that only one direction of traffic can flow at a time, preventing accidents.
That's a great analogy. And remember those exclusive areas we discussed earlier. They're also crucial for data consistency by allowing only one task to execute a critical section of code at a time. They guarantee exclusive access to shared data within that section, preventing any possibility of corruption.
So it's like having a dedicated work zone where only one person can operate at a time, ensuring that the task is completed without interference.
Exactly. Now all these mechanisms are even more critical. When we consider the challenges of mode switching, remember when the mode manager switches modes, some runnable entities might be deactivated, while others are activated. This can have significant implications for data management.
I can see how that could lead to problems. What happens, for example, to the data associated with a runnable entity that gets deactivated? Does it just disappear?
That's a great question. The RTE takes care to manage this transition smoothly. For example, it might save the data from deactivated entities to non-volatile memory, so it can be restored later if needed. It also ensures that any pending data updates are completed before an entity is deactivated, preventing data loss or inconsistency.
So it's like carefully packing up tools and materials before closing down a workstation, making sure nothing is lost or left in an incomplete state.
A very apt analogy. And speaking of non-volatile memory, this brings us to another important aspect of data consistency. Non-volatile memory, like EEPROM or flash memory, is used to store data that needs to persist, even when the system is powered off.
Right, things like vehicle settings, mileage, and other important information. That shouldn't disappear when the car is turned off.
Exactly. AUTOSAR provides a dedicated BSW module called the NVRAM Manager to handle this non-volatile data, and the RTE interacts with the NVRAM Manager to ensure consistency between the volatile RAM and the non-volatile memory.
So the RTE acts as a bridge between the short-term memory of the RAM and the long-term memory of the NVRAM, making sure data is saved and restored reliably.
Precisely. This ensures that the system can access the data it needs, even after a power cycle, maintaining consistency and preserving critical information.
This deep dive has been an incredible journey into the inner workings of AUTOSAR. We've explored the roles of the OS RTE and Mode Manager, delved into the complexities of communication, scheduling, and resource management, and discovered how the system maintains data consistency in a dynamic and challenging environment.
It's been fascinating to unravel these intricate details and to see how these software components, often hidden from view, are working tirelessly to make our vehicles safer, more efficient, and more reliable. It's a testament to the ingenuity of the engineers who designed AUTOSAR and to the power of collaborative software development.
As we conclude this deep dive, I'm left with a profound appreciation for the complexity and the brilliance of these systems. And I'm also struck by the fact that as vehicles become more connected and autonomous, the role of software and the importance of these fundamental concepts will only continue to grow. Data consistency, reliable communication, and robust resource management will be more crucial than ever in ensuring the safety and dependability of the vehicles of the future.
Absolutely. And as we move towards a future of increasingly sophisticated automotive software, the principles and mechanisms we've explored in this deep dive will continue to serve as the foundation for innovation and progress in the industry.
That's a thought-provoking note to end on. Until next time, keep exploring, keep learning, and keep diving deep into the fascinating world of technology.